And then we have some other people. Mario's in Minnesota, Philippe is in France, Richard Stanley's in Miami, and Yannick is in Venezuela. Welcome, everybody. All right, it's about time to get started. Before we get started with the speaker, I just want to remind everybody of our community statement with 3 things to keep in mind. The first is that we're all learning. And so most of our speakers have been graduate students. And so this is work that they're currently or have been, have worked on recently. And so they're learning and we're gonna learn with them about their work. The second one is everyone has something to contribute. So please make use of your chat, and one of the organizers, Galen, Alex, or myself, will chime in and ask those questions. And then afterwards, we'll have a question session. And the last one is no one has all the answers, not even the speakers. But we have people with different backgrounds and mathematical exposure. So somebody here might have an answer, or we can think of the answer together. So with that in mind, it is my pleasure to introduce Jose Bastidas, who's at Cornell University, and he will be talking to us about the polytope algebra of generalized permutahedra. And so as soon as the sharing function gets started, we will hear from Jose. Also, I guess this is a moment. Let's welcome him with a nice clap.
Okay, can you hear me now?
Yeah.
Okay, thanks Andres for the introduction, and Galen and Alex for organizing this very friendly space to talk about combinatorics. It's really nice to have the opportunity to talk here, and to everyone for coming to my talk. So the plan today, I'm going to go top to bottom in this diagram. I want to tell you a little bit about McMullen's construction of the polytope algebra of a finitely dimensional subalgebra that is relative to a fixed polytope P. And then I will focus on the case where that polytope is a sonotope. And in that case, we're going to have an additional structure of the module over the Dix algebra of a hyperplane arrangement. So I'll remind you what that is. And at the end, I'll focus on these 2 interesting cases of the permutahedron and the type B permutahedron. Okay, so let me start right away with the construction of McMullen. The polytope algebra, we're going to be working on a real vector space. And the polytope algebra of that vector space is generated by classes of polytopes. I'm going to denote them with brackets. And these classes of polytopes satisfy these relations. So the first one should remind you of the valuation relation that Marielle discussed a couple of weeks ago. Where basically we're trying to mirror this identity between indicator functions, but just with these classes of polytopes. And the second relation that we have is that the class of a polytope and any translate of the polytope are the same in this algebra. So just as a silly example, let's figure out what happens if P is a 2 simplex, and I want to think of P as this small simplex right here. I want to convince you that this identity holds. And if you see on the left side, I have 3 copies of the triangle multiplied by 2, so dilated by 2. And on this side, I have 3 copies of my triangle and a copy of the triangle dilated by 3. And just by moving things around, we can see that everything that is darker has a multiplicity, let's say, of 2. But this point, because this one is in the three triangles, has a multiplicity of 3. And once I move this point inside, it has a multiplicity of 4. And the same is going to happen in the other side if I move these triangles. Everything that is shaded has a multiplicity of 2, and this special point is in the 3 small triangles, and also in the big triangle, so it also has a multiplicity of 4. But there's an additional structure here in the polytope algebra, and that's the one that makes this an algebra, a product. And the product of 2 classes, we only have to define it in classes of polytopes, is given by the Minkowski sum of the polytope. So here's a reminder of what the Minkowski sum of 2 sets is. It's just take every point in A, every point in B, take the sum, and that forms a big set. That's the Minkowski sum. And the Minkowski sum of polytopes is again a polytope. So this is well defined. And it's easy to see that the class of any point is the unit of this product, right? If I just take the Minkowski sum with that point, I'm just translating the polytope. And because of this relation, I'm actually not doing anything. Okay, so now we can rewrite this equation that I had before, this example, as saying that the class of my triangle -1, when I raise this element of the algebra to the third power, I get 0. Here I have p cubed, so p times p times p, which means p plus p plus p, Minkowski sum, minus 3p squared plus 3p minus 1 is 0. Okay? And this is not a coincidence. It turns out that for any polytope, if I take the class of the polytope minus the class of a point and I raise it to the dimension of the polytope plus 1, I get 0. And this is really nice because it allows us to define the logarithm class of any polytope just by using the power series that defines the logarithm. And because this sum, in principle, it goes all the way up to infinity, but it's going to be finite because this element is nilpotent. I can define the logarithm class. It's just some linear combination of polytopes. It satisfies the properties that we expect. So the exponential and logarithm are inverses of each other when they are defined. And this is a really nice property that the product of classes now turns, well, if I have a product inside of a logarithm, I can take it out as the sum of the logarithms. So it has all the nice properties that we want. And the main theorem of McMullen is that this algebra is a graded algebra, and that the grading is actually given by these classes of logs. So if I take all the log classes of polytopes, that's the first graded component. And after that, I start multiplying, I get higher graded components. And this is finite dimensional, it's finitely graded, it ends up here. There's nothing in degree higher. Okay, so this is a very hard theorem, and actually realizing the vector space structure is complicated, but for now, believe me that this has the structure of a vector space. And there's one really nice operation that I want to introduce, that is the dilation morphisms. So for any scalar, I can take the dilation of a polytope, and actually this map is going to define an algebra morphism of the polytope algebra.
Jose,
yep.
Someone asked where you might be able to read maybe the proofs of these statements that you're giving.
So far, everything's in the first paper of McMullen about the polytope algebra, and it's called like that. It's the polytope algebra of McMullen. It's from '89, I believe.
Awesome, thank you.
Yes, and what I'm going to say in a couple of slides is in a subsequent paper that's called On Simple Polytopes, that it's from '93. Okay, so once we have this dilation, any scalar, I have these dilation morphisms. And let's see what happens if this lambda is very special and it's just a non-negative integer. Then the properties that we discussed about logs yield this chain of equalities. And this reduces to saying that the log class of any polytope is an eigenvector for these dilations, right? And the eigenvalue is n, is the scalar that we're scaling by. And this is clear when n is a non-negative integer. But it turns out that this is true for any positive scalar. And actually, this property characterizes those graded components. If I take an arbitrary element of the algebra, this element is going to be homogeneous of degree r if, when I dilate it by a positive scalar different than 1, the dilation is just lambda to the r times the element that I started with. So no single class of a polytope is going to satisfy this, but some linear combination might. Okay. Good. And I want to introduce that second part that I told you. So this is also definitions by McMullen, and it's the algebra relative to a fixed polytope. So let's fix a polytope P. There are two definitions that I'm going to use. The first one is what's a Minkowski summand of P. I'm going to say that a polytope is a Minkowski summand if I can write P as the sum of Q and Q prime for another set Q prime, but it turns out that if we can do it for some set Q prime, it can be a polytope as well. And the other definition is that a polytope is a deformation of P if the normal fan of P refines the normal fan of Q. So here I have an example of something that is both. Q is a Minkowski summand of P, and here I have that Minkowski complement if you want. And it's also the formation of P because the normal fan of Q, all the faces, all the cones in the normal fan of Q are unions of cones in the normal fan of P. So maybe the new one here is this two-dimensional cone right here, but it turns out that this is the union of this cone and this cone. So it is a deformation. And a key theorem here, this is a result by Shepard, is that a polytope is a deformation if and only if when I scale it by a small enough constant, it is a Minkowski summand. So basically, up to dilations, these two definitions are the same. And the original definition by McMullen of the polytope algebra relative to a fixed polytope is that this is the algebra generated by the classes of Minkowski summands. But because of this theorem, we could say Minkowski summands or deformations, and it's going to be the same. Okay, so let's say something more about this. The first thing is that because whenever I have Q, I also have the log class of Q, because this is just defined in terms of powers of Q. This is actually generated by homogeneous elements, so it inherits the grading from the original algebra. So we have also a graded algebra. And McMullen showed that when P is nice, when P is a simple polytope, so whenever I have, if P is n-dimensional, I have n facets meeting at a point. When P satisfies that property, the dimensions of these spaces are the H numbers of the polytope. So a quick reminder of what the H numbers are. They're basically a change of reparametrization of the phase numbers of the polytope. So there is an explicit way to find the H numbers out of the F numbers. And it's a combinatorial invariant of them. Okay, so now the question is, okay, what else can we say if we restrict further to the case of sonotopes? And remember that a sonotope is just a Minkowski sum of segments. So here we have an example. If we sum up these three segments, we take the Minkowski sum, we obtain this hexagon. This hexagon is a sonotope. And that's the case that we're going to focus for the rest of the talk. So any questions so far? Okay.
I have one question from,
yep.
if you go back a few slides, one thing I was curious about is, so you have this Q and this Q prime, and so certainly if Q is a Minkowski summand, then the Q prime is going to be a Minkowski summand. Is it always true that if Q is a deformation, then that particular Q prime is also a deformation? I'm just curious.
So in principle, if I say rescale this polytope Q by a factor of 5, and I get something huge here, this polytope is no longer a Minkowski summand of this, right? It's too big to fit inside. But a small enough dilation will be, and the corresponding summand is also going to be a deformation. That's a very good question.
So you can make it too big, but if it's small enough, then it is, and the corresponding one also is a deformation. Okay. Yes,
exactly. And the key property there that I'm not mentioning is that we can say what the normal fine of a sum is. The normal fine of the Minkowski sum of two polytopes is the common refinement.
Oh, okay.
And therefore, yes, and therefore the other summand is also a deformation.
Okay, cool. Thanks.
Okay, so yeah, let's keep talking about the case of a fixed sonotope. And let me remind you of this notation. Whenever I have a polytope Q and a vector V in the space, I'm going to use this to denote the phase of Q that is maximized in the direction of V. And this is what this formula is saying. And in general, if P is the Minkowski sum of two other polytopes, Q and Q prime, moving now. Okay, I think it's fine. When I maximize in the direction of B, this relation is preserved. So still the phase maximized in the direction of B of the polytope P is the phase maximized in the, of Q plus the phase maximized of Q prime. And if we just call F for now to this phase, we see that Minkowski summands of P, when I apply this map, go to Minkowski summands of F. So in principle, we have a map that goes from the algebra relative to P to the algebra relative to F, a phase of P. And this was already defined by McMullen. He noticed that when P is a simple polytope, these morphisms are surjective in general. But in the general case, they are not necessarily surjective. And what's special about sonotopes is that faces of a sonotope are also Minkowski summands. So that's very special, and that's unique of sonotopes. I mean, if every face is a Minkowski summand, then the polytope is a sonotope. And that gives us inclusions of algebras right here. So this doesn't happen in general. This doesn't hold for general polytopes, but it does for sonotopes. And this is also going to imply that this morphism is surjective for sonotopes in general. Not only for simple ones, but for general sonotopes, these morphisms are surjective. But the key property that we want to study now is that we have this composition of maps, and that sends an element of the algebra of this polytope P to the same algebra. So we have an action of the faces of the normal fan into this algebra. And that's what we want to study next. So let me introduce some notation about hyperplane arrangements, because key point here, the normal fan of a sonotope is or corresponds to the faces of an hyperplane arrangement. And that's what we want to study now. So let me call A to a hyperplane arrangement, central, finitely many hyperplanes. L is going to denote the lattice of flats of the arrangement, so all the intersection of some hyperplanes in A. And sigma is going to denote the set of faces of the arrangement, so the cones that I see in the picture. They are the faces of the closed regions. So those are the maximal faces, and every face of that cone is a face of the arrangement. And it turns out that this set, this finite set, has the structure of a monoid. So there's a product between faces. The idea is that if I take a point, if I want to multiply f and g to faces of the arrangement, I take a point in the interior of f, a point in the interior of g, and I walk on a straight line. And as soon as I move a positive distance from f to g, I'm going to be in maybe a different phase, maybe the same, and that's the phase f times g. So as an example here, I have a three-dimensional arrangement, but I'm intersecting it with a sphere. So all the picture here is in the surface of that sphere. Here the phase f is actually an infinite ray. And when I walk from f to g, one observation is that both faces are contained in this hyperplane. So if I walk on a straight line from 2 points inside of a hyperplane, I'm not leaving that hyperplane, right? So the product fg is going to be contained there. And it's not hard to see that if I start walking in that direction, this is the phase that I land, fg. And something similar can be argued here. So f and g are not contained in any common hyperplane. So it turns out that the product has to be contained in no hyperplanes. It's going to be one of these maximal regions. And we can check that it's actually this f times g right here. Okay, so there's a lot of interesting things to say about this product. But for now, what I'm going to worry about is about the linearization of this monoid. This is what's called the Tits algebra of a hyperplane arrangement. So now I'm going to take linear combinations of bases of the arrangement. And what we discussed before was that this polytope algebra, when P is a sonotope and the normal fan of that sonotope is given by A, is a right module over this algebra. And this is the product. If I have any class of a deformation of P, and I act with the phase F of the hyperplane arrangement, what I'm doing is maximizing in the direction of that phase. So for example, this is my sonotope P right here, and Q is a deformation of P. If I maximize Q in the direction, of this phase F, I have precisely this phase of Q. If I maximize, for instance, in any direction given by G, so this is a chamber of my arrangement, I could take any, this could be this small vector right here, should be from the center, or this bigger vector right here. As long as it's in the interior of G, this is well defined. And I can see that the phase of Q maximized in that direction is this point right here. So this is Q maximized in the direction of G. And I take the class of that polytope. You have to check that this is associative, and this is not too hard. But something interesting is that because dilations, or positive dilations at least, commute with this action, right? I can first maximize in this direction and then say dilate by 2, or first I could dilate and then maximize in that direction. The grading is going to be preserved, or not only that, but each one of these, because they were the eigenvectors of the dilations, each one of these is going to be a submodule. So actually this decomposition that we had in graded components is actually a decomposition into right modules. So this is nice because this helps us understand the structure of a module a little bit better. But we want to do more. We want to now understand the structure of each one of these modules. So that's what we're trying to do next. What is nice about the TITS algebra is that we know what all the simple modules are. So there's one isomorphism class for every flat of the arrangement, and each one of those simple modules is one-dimensional. The action is actually pretty simple to explain. So in this module, all the faces contained in X act trivially, so they don't do anything, and all the faces outside of that flat annihilate the module. So it's a very simple action, but let's not worry about those too much. What I want to know for these modules is, ideally I could write these modules as a direct sum of simple modules, but that doesn't happen always. So the next result, the next thing we can hope for is that I write a decomposition series of my module. So I have a chain of modules such that every quotient is simple. Another question is, what modules appear as quotients? And that's what we're gonna try to solve today. So I'm going to use this notation, eta sub x, where x is a flat of the arrangement of this module, denotes the number of composition factors, so these quotients, that is isomorphic to the module indexed by that flat x. And the first result here is that there is a way to compute these in general. So Ayer and Mahajan, in their book, they study modules over the TITS algebra in general, and they know that we can find these numbers via this formula, where mu is the Mobius function of the arrangement. So this is something that we can compute. And then we have to compute the the dimensions of these submodules. Okay. These are not submodules, but subspaces, linear subspaces. And the result with what I told you before about the surjectivity of the maps for sonotopes implies that these dimensions are actually easier to compute than we think. We can explicitly say what they are. So they are the dimensions of these subalgebras, or the graded pieces of these subalgebras. And in the special case where the sonotope is simple, then McMullen's formula is going to tell us this is just the H numbers of that polytope. So let's go to that case. So for now, just remember that we have an explicit way to compute these dimensions if we have enough information about the algebra. Okay. And a very nice case, of course, is the case of the permutahedron. So let's discuss about the braid arrangement first. The braid arrangement in RD has all the hyperplanes xi equals xj, or I different than j. So for instance, in R3, we have the hyperplane x1 equals x2. This is x2 equals x3, and x1 equals x3. And the picture that we have here is just, well, first of all, this hyperplane arrangement is not essential. That means that the intersection of all the hyperplanes is not a point, it's actually a line. So we're gonna intersect with something orthogonal to that line. And then we're intersecting with a sphere. And that's the picture that we have here.
We have a question from Vic Reiner. Was it clear that those HRs that appeared wouldn't depend upon the face inside Y that you chose?
Okay, that's a great question. So for sonotopes, what it's nice is that if I change what face I take inside of the so first I'm taking a face of the arrangement that is maximal inside of this flat. If I maximize my sonotope in that direction, in the direction of every one of those faces, I get different faces, but they are all translates of each other when the original polytope is a sonotope. So that's why this is independent of what face I pick. And actually in the algebra, translation is nothing, right? A translate of a polytope is itself, or has the same class, the same representative. Okay, thanks. Yes, so going back, we have our braid arrangement, and a very nice polytope, of course, is the permutahedron. That is the convex hull, or is the polytope whose vertices are all the permutations of this point, the point that has coordinates 1, 2, all the way up to n. Sorry, this should be d, just like the space. It is a simple polytope, so that's nice. It has dimension d-1, and we actually know what the H polynomial of these polytopes are. So I'm sure that for the polytope, this might be an earlier result, but Brent in '94 he computed the H polynomials for all Coxeter permutahedra. So that's why that's what I'm putting Brent here. But I'm sure that maybe someone computed it before. And just to picture what the permutahedron looks like with respect to this picture, basically these middle points in the chambers, they correspond to those permutations. So maybe this is the point 1, 2, and sorry, 1, 2, and 3, and this is 1, 3, 2, and so on. And the permutahedron is just the convex hull of these points. So the two-dimensional one that lives in R3 is a hexagon, but the three-dimensional one that lives here, I cannot do the full picture right now, but we can see that it has some faces that are hexagons, just like the previous one. It has some faces that are squares, just like the product of two intervals. So the face structure of these polytopes is very nice. We know what happens when we maximize in any direction. But going back to this definition, we know what the H polynomials of these polytopes are, and they are given by the Eulerian polynomials. That in principle are defined, way before they were defined by Euler. And that are, let's say, a common characterization of these polynomials is that they keep track of the number of descents of the permutations. It turns out that in type A, descents and exceedances are equivalent, are equally distributed. So I'm going to give the definition in terms of exceedances. And remember that the exceedance and exceedance of a permutation sigma is just some position I, such that when I apply the permutation, I get something strictly bigger. So of course, D itself cannot be an exceedance. There is nothing bigger than D. And the number of exceedances ranges from 0 all the way up to D-1. Okay. And now the key observation is that the permutahedron is a sonotope of this arrangement. So I'm not writing it as a Minkowski sum of segments, but this can be done. And therefore, the polytope algebra of the permutahedron is a module over the Tietz algebra of the braid arrangement. And that's the structure that I want to discuss next. So the main theorem here is this. We can give the dimensions of these spaces, or we can say what these numbers are. So for any flat x of the braid arrangement and any graded any degree, so from 0 all the way up to D-1, the number of copies of x, or the module corresponding to x in this graded piece, is counting the number of permutations with exactly r exceedances and whose fixed space is x. What do I mean by that? So the permutations naturally act on RD by permuting coordinates, and the fixed subspaces are precisely flats of this arrangement. So if I take any permutation, I can wonder what's the largest flat that is pointwise fixed by this permutation. This is what we mean by the support of that permutation. So there's an explicit formula here. And an observation that I want to make is that this definition that I just gave could be said in a different way, because there's this correspondence between flats of the arrangement and set partitions of D. So a set partition of D is just a collection of subsets of the numbers 1 through D, whose union is D, or the whole collection of numbers, and they are disjoint. And the correspondence is really easy. So the intersection of some of the hyperplanes of the braid arrangement is going to force some coordinates to be the same. And I'm just putting those coordinates that are forced to be the same inside of the flat in the same block of the corresponding partition. Okay, Jose, that's what I'm doing.
Jose, Yannick yep. asks, is S of sigma the destandardization operator?
No, I don't believe so. No. I don't think so. Yeah, no, because S of sigma is a flat, right? For now, we're identifying with a flat of the arrangement. And my point here is that we could also define it as a partition, and it's going to be the partition underlying the cycle decomposition of sigma. So for instance, if sigma was this permutation, so I'm writing it in cycle notation, then S of sigma, the support of this permutation is precisely this, right? I just have the cycles, and these correspond to the blocks of my partition, right? And it's easy to see if I act with this on RT, because the first coordinate moves to the fourth, and if a point is fixed under this action, the first coordinate and the fourth coordinate have to be the same, and the same can be said for the fourth and sixth, and so on. Okay. So this is the main result for type A. I want to discuss some particular cases of this. So what happens if I want to count these numbers when I have 0 exceedances, so the 0th degree of my algebra? Well, it's easy to see that there's only one permutation that have no exceedance, right? Because I need to send every number to something that is less than or equal. And because sigma is a permutation, that's going to force sigma to be the identity. That's the only option. And okay, so we know that this dimension is 1 only if the flat is the maximum flat. So where every block is by itself, every element is one block of the partition. And actually, maybe I'm going to skip. No, I think we have time. And actually, this is really easy because this space is always generated by the class of a point. And the class of a point is fixed by everyone, right? If I maximize the point in any direction, I get the point. And this is precisely the definition of the module associated to the top dimensional flat. Is fixed by everyone and annihilated by no one. So this is a really simple case. The other extreme case is in the maximum dimension. So what happens if this is d-1? Now I want to count permutations that have exactly d-1 exceedance. So the maximum possible number of exceedances. And if you think about that for a second, you're going to realize, okay, then I need to send 1 to 2, and 2 to 3, and 3 to 4, because that way I maximize the number of exceedances. So there's only one permutation with d-1 exceedances. And because that permutation is what we mentioned before, 1 goes to 2, goes to 3, goes to 4, all the way up goes to d, then the flat that is fixed by this permutation is the minimal flat. All the coordinates have to be the same if I'm fixed by this permutation. So again, there's only one such subspace, and yes, it is true in general that the maximum weighted component has dimension 1 always. And actually here, the opposite happens. So this is not an obvious statement, but I mean, it is true that if I act with any phase other than the unit, so other than the minimal phase of the arrangement, on any element of this graded piece, I'm going to send that to 0. And this is precisely the definition of the simple module indexed by the minimum flat. It is fixed by the minimum element and annihilated by anything else. Okay. But maybe a more interesting case is the first graded piece. This is a very important space. This space has a lot of information about the deformations of the polytope in general, or especially when this is simple. So this is a very interesting space. Let me introduce some notation first. I'm going to say generalized permutahedron for deformations of the permutahedron. So basically the elements whose classes are in this algebra. And I'm going to use the notation delta J, where J is a subset of D, to denote the simplex whose vertices are the basis elements indexed by J. A key result here by RD11 and Etienne Docker is that every generalized permutahedron can be written uniquely as a signed Minkowski sum of simplices. So what does it mean, this signed word over here? Well, it means that for every generalized permutahedron, there's a unique choice of scalars, positive and negative, such that this equality is true. So this equality is in the world of polytopes, Minkowski sum of polytopes. I can take this Minkowski sum of polytopes, where all of these are the positive constants. I can take the Minkowski sum of these polytopes, where I take the negative constants and I just make them positive. So I have two polytopes. And this signed Minkowski sum means that Q plus this term, or plus this polytope, equals this other polytope. That's what it means by Minkowski sum, by signed Minkowski sum. And the nice thing about this is that, well, just apply. So we know that Minkowski sum corresponds to the product of this algebra. So just take the classes of all the polytopes here and apply logarithm to that. The logarithm of the product is the sum of the logarithms. So we have this identity. We know that the log class of Q can be written as this linear combination of the log class of these simplices. And because this choice was unique, this is going to imply that these elements are a basis for this space. Okay. There's one catch, of course. Here I'm taking the simplices that are at least one-dimensional, because if I take a vertex and I apply log to that, log of 1 is 0, and the same is true for the log of the class of a point, that's 0. So other than those, these elements are non-zero, and they form a basis of this space. And actually, if we use our previous theorem and we try to compute the dimensions, we get this. So how can I get exactly one exceedance? Well, if you think for a while, if you have any cycle, every non-trivial cycle is going to have at least one exceedance, right? Because you're moving A to B, B to C, and at least if they're not all the same, one has to go to something bigger at some point. So the only way to have exactly one exceedance is that I have only one cycle, and all of the others are by itself. I can have fixed points, but only one cycle. And in terms of the underlying partition, that means that my partition has only one block that is not a singleton. Okay. And if I identify my my flat with that block that is the non-singleton block, I have this correspondence between these spaces and these elements that form a basis. And here, maybe we don't want to think too much about this right now, but this is somehow giving us a clue of what decomposition we want to write for this module. So what's the word's escaping me right now, but the chain of modules that we want to write so that the quotients are simple. How to do it is basically encoded by this equation right here. Okay. Now I want to go further and discuss the case of type B. Maybe there's a little bit less information, but still very interesting. So first, what's the hyperplane arrangement here? I have the same hyperplanes of the braid arrangement. So for example, x equals y, but I also have all the coordinate hyperplanes. So y equals 0, x equals 0. And I also have these hyperplanes that look like the ones of the braid arrangement, but with a negative sign. So y equals negative x, for instance. I have those arrangements. And the permutahedron now is going to be the convex envelope of the sign permutations of the numbers 1 through d. So here, for instance, I have the point 2, 1, but then here I have 1, 2. Here I have the point 2, negative 1. Sorry, I think there's a lot of noise here. I'm sorry. And I take the convex envelope of all of this. So I have here a octagon. And just like we had with the permutahedron in dimension 3, when I take the type B permutahedron of type B, the 3-dimensional one, I'm going to see faces that look like octagons here, so like the previous type B permutahedron. But I'm also going to see faces that look like hexagons right here. So they are like type A permutahedron. And this is very nice. The type B story always encodes the type A story. So that's very, very nice. This, of course, has nice properties as well. It's also a simple polytope. And the H polynomial is also encoded by the Eulerian polynomials, but in this case, the Eulerian of type B. And this result, again, the H polynomials, this is a result of Brenty. But the description that I'm using here, the fact that this statistic that I'm going to define in a second is the same as the usual descents for Coxeter groups. This is a result of Fuat and Han, a relatively recent result, okay? Because this is actually a relatively recent statistic. Okay, so let me define all these things here. First, the group of sign permutations. So a sign permutation is just a permutation of the numbers 1 through d under negatives that satisfy this property. So if I send the element I to j, then negative I has to go to negative j. And here's an example of this. So just for instance, I'm writing this in cycle notation. So I'm saying 4 goes to negative 3, and therefore negative 4 goes to positive 3, right? And if you check that with every entry, so for example, 5 goes to 6 and negative 5 goes to negative 6, this satisfies this relation. So this is a type B permutation or a sign permutation. And I want to introduce some statistics here. So there's a bunch of different ones. I'm gonna need these three. The exceedances, just like before, this is defined, and it has the same definition as for type A. So it's all the positive entries that go to something bigger. And in this example, it's easy to see. So what's something positive that goes to something bigger? 3 goes to 4 in this cycle. So that goes to something bigger. 5, that goes to 6, but that's it, right? Nothing else that is positive goes to something bigger. So I have 2 exceedances in this case. The negations are positive entries that go to something negative. So I can check that 1 is a negation, 4 is a negation because 4 goes to -3. 6 is a negation, goes to -7, and 7 is a negation, goes to -5. So I have 4 negations, if I'm correct. Okay. And then the number, or this statistic that is type B exceedance, for now I'm gonna call it, would be for this particular case, 2 plus 4 exceedances plus 1 divided by 2, and then I take an integer part here. So it's kind of mysterious that this statistic works, but it does, and this is 4. So in this case, the exceedance of type B of this particular permutation is 4. And what is the result here? So it's very similar to what we had before. For any flat of the arrangement and any degree, any graded piece, this dimension is counting the number of signed permutations that fix that flat and that have exactly R exceedances of type B. Okay. So here's a sum up of a bunch of things that were going on behind the proofs. So generating functions for these polynomials are known. For the classical Eulerian polynomials, this was known by Euler back then. And for the type B Eulerian polynomials, this was also found by Brenty. And we're using that. We strongly use these, well, at least that we know these formulas for the generating functions, and here they are. But the proofs of our theorem allows us to do something cool, because we can ask for, okay, what are the double generating functions? So I want to keep track of the 2 parameters, the dimension of this space and the number of exceedances. And with the proofs of the theorems, we can do that. So we can recover this result. For instance, this was already figured out by Brenty, that if I take this double generating functions, or you keeping track of exceedances and of the dimensions of this, is just this generating function to the tth power. And this was known. This was known because I could replace this by saying the number of cycles. This is the discussion that we had before. So the dimension of this space is actually going to be the same as the number of cycles of that permutation. So this was known. But I believe that this is something new. If we do the same for type B, if we ask about the dimensions of those flats of the type B arrangement, the generating function that we get is this product. So where B is this one over here. And this is always the case whenever we have something of type B. Somehow there's a shade of what's happening in type A. So type A always appears inside of type B. And I want to point out an interesting corollary of this, and is that we can actually, from this definition, so we have explicit formulas for these functions, we can figure out that this space, so if I see the first graded component, so I told you that this says a lot about the deformations of the polytope, and I see how many, or I see the number corresponding to the minimum flat, this number is always 2 to the d. And maybe this sounds a little bit mysterious, because there's a lot of things that I haven't had the chance to tell you, but this is going to imply that if I want to have a family of type B permutahedra, or generalized permutahedra, that I can use to write any other type B permutahedra as a signed Minkowski sum of those, I necessarily need to have 2 to the d full dimensional ones. And this is the fact that this is the minimum flat corresponds to me saying that those are the full dimensional ones. There's like this inversion of the degrees of the hyperplane arrangement and of the algebra. So I think that's very interesting, but still there's a lot of questions open in this direction. And hopefully, if we have the chance to discuss this topic again, there's another piece that I left outside, and is that for the braid arrangement at least, these algebras can be ensembled in a Hopf monoid of species. That turns out that it's a quotient of the monoid of the Hopf monoid of generalized permutahedra of Aguiar and Ardile, but it's also contained in another geometric Hopf monoid that has been studied before. So there's also a lot of interesting things to explore right there. And with that, I want to finish. So thanks a lot.
All right, let's thank Jose. A nice talk. Are there any questions? And for the sake of the recording, feel free to unmute yourself and ask. Oh, Vic just asked a question. Vic, do you want to ask it for the sake of the recording?
Sure. It was a really beautiful talk, Jose. I enjoyed it a lot.
Thank you.
So in type A, you had these bases for that first graded part of the polytope algebra for these set partitions that had only one non-trivial block. I think those are the modular elements of the intersection lattice. I might be misremembering. Does that happen in type B again?
So there's a problem there because so what happened in type A is that when this was 1, and I have a flat here, these numbers were either 0 or 1. So there was one basis element corresponding to that flat, or I didn't have to worry about that flat at all. But what happens in type B is that we see that that's not going to happen anymore. So to a single flat, I need to be able to assign more than one generator. And actually, yeah, I don't know of any nice basis for this space, because this is a question that, and sorry I didn't mention that before, I was going to, but I forgot. This is a question that already Ardila, Castillo, Ure, and Postnikov asked in the paper about Coxeters of modular functions. So they know this result, well, the result by Ardila, Benedetti, and Docker, that the simplices generate, or in this deformation sense, they generate all the generalized permutahedra, but they don't know in general how to give explicit generators for other types, in particular for type B. So this observation was aimed to that question, that if we're going to find one, we know that we're going to need at least 2 to the D full dimensional ones. So it is not possible to just do it like in the type A case, where I just have this simplex and all of its faces. That's not going to happen here. I cannot pick just one polytope and all of its faces, because I'm going to need 2 to the D full dimensional ones at least. Yeah.
Thanks.
Awesome. Any other questions? I don't see any in the chat, and I don't hear it. So
if I have a little more time, I had one extra slide just in case.
So I'll ask, what is that extra slide, Jose?
So this is what I wanted to show you. I'm not going to have time to explain all of these, but a key property of the proofs behind this is actually just not the usual exponential formula. So a key property of exceedance is that descents don't share, and that's why these results cannot be stated in terms of descents, but only in terms of exceedances, is that whenever I have the cycle decomposition of a permutation, the number of exceedances of the permutation can be seen on each one of the cycles. So this equality that I have here, the total exceedances, I can find it on each of the cycles. And that implies that I have this equality between generating functions. So if I take all the permutations that fix some space and I see what the number of exceedances of those permutations, I can write this as this product. When now this product goes over cyclic permutations. That's what C means. And basically, whenever I have something like this, whenever I have some invariant that I can compute in terms of a partition of some set, there's this relation between all of the elements and the reducible ones that is given by the exponential formula. So if I have the generating function for the irreducible ones and I take the exponential of that, I get the generating function for all of the elements. And that's going to imply that basically for these cyclic ones, if I want to find what the generating function for these statistics are for all possible dimensions, I'm going to obtain the logarithm of that power series that we had before. And this is the classical exponential formula. In type B, it's not so clear. Or I don't know if there's a nice definition of a type B exponential formula, but we try to give one in the paper. There's one definition of a type B exponential formula. And this is the analogous right there. So for a type B or a side permutation, we can also decompose this permutation in some blocks that are not necessarily just the cycles, because here I'm using two cycles in the same part. But I can see there's a natural way to decompose them, and I can compute type B exciences as type B exciences of this irreducible part of type B, and natural exciences or standard exciences of these parts that are of type A. So here again, we see this mix between type A and type B. And if we want to do the same thing, or we want to see the generating function for the type B permutation that fix a given flat, we have this product again. So we have something that is of type B and something that is of type A. That this is just a restatement of what I had here before. And the type B exponential formula is going to give me this result right here. So if I want to find the type B irreducible ones, so the ones that only fix the origin, and I want to see the generating function for those, I have this weird thing. So it's a quotient. And this is the analogous of the type B exponential formula, because here the statement is that if I have a generating function counting something for irreducible elements, then for all the elements is going to be the exponential of that. But in type B, I need two ingredients. I need to count the irreducible for the part B and the irreducible for the part A, and then to count the not irreducible, so everything. The result is this, is f to the exponential of g divided by 2. And this is where all of this is coming from. So I think it's also a very interesting thing to look at.
Awesome. Are there any, so like you talked, this is all about like the polytope algebra of generalized permutahedrae. Are there other, classes of polytopes that you've explored the polytope algebra for, or that other people have explored it for?
I'm not sure. I kind of found a lot about it. So McMullen did a lot when the polytope is a simple polytope, but that's just the algebra structure itself. This structure of a module over another algebra, at least the one we define, can only be defined if the polytope is a sonotope, right? So I don't know how many people have tried to explore this Tits algebra and modules for the Tits algebra. I think that this is pretty new.
Mm-hmm. Awesome. Yeah. All right. Are there any other questions? All right. Before we thank the speaker one more time, let me just invite you all for next week. Next week's GOCC will be by Sarah Bronner from the University of Minnesota, and I'm not exactly sure what she'll talk about. Sarah, do you have an idea what you're talking about? Not to put you on the spot. If not, then come in next week for a surprise.
Yes, I will send you an abstract soon.
Awesome.
I have one. I'm going to be talking about Eulerian idempotence of real reflection groups and the representations that they generate.
Awesome. That sounds lovely. So we invite you all for next week. So Sarah will be talking to us about that. But yeah, let's thank Jose one more time.
Thank you.
All right, I think we'll stop recording.